Okay, I know we're running late now, so I will go ahead and kick this off. And thank you so much to McCool in the room there, who's leading this, and as well as Bob Gradick, and Jennifer Way is helping us as well. So yeah, this session is on informing decisions around climate risk. We're going to give some examples from global to local applications using NASA Earth data. The goals of this session are to identify and address the needs of stakeholders by incorporating technology through directly and through intermediaries. You're going to hear some examples of that and how to overcome barriers to do that, and then discuss best practices for co-producing solutions with stakeholders to inform their decisions. So the session includes Bob Gradick from Western Pennsylvania Regional Data Center. He will kick us off. McCool Sonwalker from SSAI and NASA Goddard will present next. And then we've got also Mish Tatsubori from IBM. That's an important public-private partnership we have. And then Grace Llewellyn from NASA JPL. So with that, I will let Bob go ahead and start, and I will mute myself and turn off my speaker. Thank you very much.
You're the
I'm the Google.
okay, cool.
Somebody just frantically waited about 8 minutes. That way I gotta wrap it up.
Yep.
So hi, it's good to be here with you up in Vermont. So I'm at the University of Pittsburgh, and I'm going to talk about developing relationships with data users, and wrap up with discussion of barriers and maybe some suggestions that I have for overcoming them. And there we go. Whoop. There we go. Okay. So I work at the University of Pittsburgh. The project I manage, Western Pennsylvania Regional Data Center, is the Civic Data Intermediary. That's actually a partnership with University of Pittsburgh, City of Pittsburgh, and Allegheny County. And so what we do as an intermediary, we kind of help people use data and help people publish data. So we provide an open data infrastructure. So we actually use open source software for that, CCAN, which is the same as data.gov. We provide data acquisition and transformation services. So we're setting up a lot of data pipelines from our two partner organizations and making those publicly accessible. We develop a lot of different tools and dashboards to help answer questions and inform issues. We support different community initiatives, like, for example, the Complete Count Committee and initiatives around lead safety and other things, and also provide project-based assistance to special projects. Do a lot of technical assistance work, answering questions, responding to requests, and then have been doing a lot of work around data literacy training as well. This is me when I'm working with Earth science data. So I look a lot like Patrick Starr, and so you can see the tools that I have, and the data is actually, I don't even know, the bench maybe, but that's kind of how I feel in a crowd like this. So I'm not faculty, I'm staff, and I kind of just manage this project that has a lot of different data sets. But I wound up here because Stephanie, whom you've seen earlier, her son goes to Pitt, like my son does, and she was dropping him off and met somebody from kind of our whole Earth science operation, and they made a connection to me saying, hey, you should talk. So we started to talk, and then we started to talk more about use cases for local Earth science data applications, and then connected with McCool. And the next thing, we're on a call with our city and county data stewards to talk about, like, what do you need? What kind of Earth science data could help inform your work? And now where we are right now is McCool is working with David Walker from our team to set up a whole lot of data pipelines. And then we're going to talk more about where we're going with that. So we're organizing around these use cases. Landslides. We have really unstable soil, a lot of rain, and lots of hills. You might have seen it last year at this conference. That's actually a road that fell in. on an apartment building. So our county has a landslide task force. So they're working with local governments to kind of get them ready for landslides. And so they have a data portal that has some landslide data. They also have 911 call data that goes with it. So we've identified a few data sets you can see there. And just in the interest of time, I'll not read through all of those, but lots of good stuff that we didn't know about. We also have pretty terrible air quality compared to a lot of other places in the US, and not just from wildfires. We have a lot of legacy emissions, and a lot of stuff just blows over us. We do maintain the data feeds for our county's air quality monitors. There's a big, robust effort locally to do crowdsourced and open science data collection. But there's a lot more there that people aren't really using. And the suggestions from the NASA team have been outstanding. And so these are the data sets that David and McCool are working on, or at least some of those. And so we hope to bring this into the efforts to improve health and kind of inform different aspects of this work. So we do a lot of work with researchers at our university and other institutions too. So we see a lot of flooding too. Impacts of climate change are big. We had a floating dumpster a few years ago that made the news. People even added like flames into the dumpster. It was great. But we're looking at data like the First Street data to help our city and county plan for climate change. So kind of understanding where they could put the investments to mitigate the impacts of climate change, whether it's planting trees in the right places to address heat islands, or what kind of infrastructure do we really need to mitigate the aspects of like urban flooding that we face a lot in a lot of communities. Oh, and one thing is also having conversations with people about that. The local impacts of climate change data can be a really useful tool for informing that. And then we can also talk about environmental injustices along with that too. And the last application I want to talk about is just the city's replacing its streetlights with LED. And they're really interested in equity impacts of that. So they want to see if they're actually putting lights in places that maybe haven't seen the investments that they should have seen over the years. And so being able to use satellite data from Black Marble will be really important in that. We also have a dark skies ordinance, and I know researchers at Carnegie Mellon up the street from us are using this data as well to see, are we actually able to see the stars? And so some other use cases we've talked about: counting the number of trees to see how much carbon capture is taking place. Can we measure quality of the water in our rivers through imagery? And can we talk about performance and sustainability too? And so we're going to make use of this data once we get it all together in the next phase of our work, and I'm looking forward to that. But some barriers that we face in applying earth science data in local communities. That's what I'm going to talk about now, and I'm going to share some suggestions on how to overcome that. So being aware of data that's out there is one barrier. So what exists? Where can I find it? Is this data relevant to me? Can I trust it? What can it be used for? And is there somebody that I can talk to about it? And so some ways to overcome that, just based on our work of doing this deep relationship work with local organizations and local data users, really is important to connect with communities of practice. So we are out there going to different meetings. Our city and county data stewards are going to meetings. Our university partners are going to meetings. They all want to use your data. So go to those meetings, go to those communities. The big one for us is the National Neighborhood Indicators Partnership. There's a lot of others for chief data officers. There's librarians. There's public health workers that are interested in things like social determinants of health. Engage people from all across academia, not just the researchers. Go and work with your data librarians. And also look for projects like ours and other universities. They do exist. And I would recommend connecting with them. Technical assistance is really vital. And so think about technical assistance, not just from, are we doing stuff, but look at the user's perspective. Can they find your services? Can you go to the NASA website and know exactly where to reach out to people? Heard a lot about great things today. I just didn't know about them. And then engage people organized around different initiatives. So whether it's around social determinants of health, UN Sustainable Development Goals, we're in countless meetings talking about how do we measure the impact of sustainable development And there's just like a lot of questions that people have about that. And you can help provide a lot of those answers. Data accessibility is another set of barriers. So this is where David's work with McCool has been really important. So sometimes we need to build tools to extract data from large scientific data sets. They want to use their own tools, but sometimes they run into things like unfamiliar file formats, and end users have limited capacity to use that data. And so, work to develop tools to make that data more accessible, open source those tools, capture feedback from potential users, user test your tools and see what kind of experiences people have with that. Again, technical assistance is really important. People want to trust somebody that's talking to them. And then engage with your open source software communities to make sure that the software that you do build and use better meets your needs. And I'd actually like to do an unconference session about that later this week. And then the final set of barriers is just really around the lack of context. So where does the data come from? What does it mean? How can I use it? How shouldn't it be used? And I'm not a scientist. How can I explain it to somebody else? And so there's a lot here. I just kind of put this here as just like some of the contextual information that's important about data. So we've been able to write guides for some of the administrative data that we get, but these are some of the questions that you can answer through your own documentation. And then again, technical assistance, help people out when they need it. And that can be done directly or even through networks like those communities of practice. And so this is how you can reach me. I'd love to chat about building communities around data, and hope to, I did put an unconference session on for later this week. So happy to talk. Thank you. That's an actual photo.
Hey, good afternoon, everybody. I'm Mukul Sanwalkar. I'm a data scientist working with Stephanie and the Applied Sciences team at NASA Goddard, also representing SSAI here. So what I'm coming from in terms of my work and also in how best we could, are you able to hear me now? Okay, is this fine? Can you hear me okay? Yeah, okay, thank you for pointing that out. So my work primarily involves working with stakeholders, external stakeholders, also NASA internal stakeholders and science teams in trying to understand what science products can be delivered to external stakeholders, in what ways, and just the whole ecosystem around the data pipeline that could be put together for such data transfer. So I'm going to kind of first start off with the big picture, which is climate risk and how does it affect communities. And that's where we kind of have our first baseline of information that we want to start collecting. So climate risk, as you all know, is more about being able to quantify the unknowns in climate forecast models. So the models exist. If we can identify the unknowns, then we can share them appropriately and in a timely fashion. And most of that work is already done by the now universally accepted shared socioeconomic pathways. These are the 5 narratives that all the international climate scientists and economists, they came together and put together almost like a timeline of these are the narratives for the society for this 21st century, and we need to follow these pathways in order for certain outcomes to happen to the society in general. So in applied sciences on our side, we are shrinking that global view into a smaller picture, as in, we are to identify what communities will be affected by climate change. Okay, and what are those risks? Can we quantify them? Can we create products out of it? And can we eventually co-produce these solutions with local communities? And the purpose from the local community's point of view is, once we get this information, can we aid that, or can we assist our team in decision-making, in informed decision-making? And this transaction has to happen. Of course, there are various means, but we are leaning towards the path of OSSI, which is open source software infrastructure. And there, of course, there's a thin line between open science and open source science. I'll just have my comments on that towards the end. But in general, we're using open source science as means to delivering that relationship. So climate risk models are mostly done. Again, I'm no expert in it, but generally speaking, there are methods and techniques with underpinnings in statistical data modeling, simulations, probability theory, and machine learning. And the common theme amongst being able to solve problems across these various domains is prediction. Is you would want to predict the risk given the variables that govern climate variability using current and historical data records. Now here, the prediction of risk doesn't necessarily meaning giving it a value, a numerical value, but for communities, it's mostly about the likelihood of certain things happening or the odds of certain things happening, which is slightly different than just a pure probability number, right? We also need to know the climate risk ahead of time. So science teams at NASA Goddard and various interdisciplinary teams are working towards the approach of mitigation and adaptation by using the various Earth observing satellites we have and the data products that come out of it. So mitigation is all about trying to reduce the effect due to greenhouse gases, and adaptation is all about, what do you understand about the local population and economics so as to reduce the impact due to climate change. So here are some of the examples of how NASA products and satellites and instruments are, putting the mitigation up at the forefront. And thinking of mitigation is, again, a good analogy that I'd heard is imagine your car, and the brakes are basically the mitigation. We're trying to slow the effects due to greenhouse gases. Whereas adaptation is more like, like airbags in your car, which would try to reduce the impact due to it. So some of the examples of the products and instruments that would go a long way in mitigation related studies would be MERA2 products, which is reanalysis product, GEOS forecast model, 5 and 10-day forecast, which is S2S, which is longer. Then iMerge product, which is precipitation related, again, easily available for access, in public's domain. There's also a specific greenhouse gas emission related measurement instruments, O3, TROPOME, and GOSAT. Drought and flooding products, which is MODIS, near real-time product. They have the soil moisture and analytics crop CASMA, which is like a downstream product that can also be used. Included is also surface mineralogy related EMIT product. So these are just a flavor or example of how mitigation and data specific to mitigation can be used. And on the adaptation side of things, a few things are still similar. Some of the other ones where you have to get into account the changes to the land, use land cover, including Landsat, VIIRS, again, a lot of these downscale level 5 products and above and beyond are also available. There's nighttime lights, which Bob just mentioned, monthly changes to Antarctic ice mass grace. Again, still very relevant in terms of what final products or what downstream products it can produce. Drought flooding with MODIS and RT, and also Earth surface water, the newest SWOT mission. Okay. So now the challenge is, what action are we taking, knowing that we have the data available and we have to do mitigation adaptation in tandem or in sequence or based on how the community needs are progressing. So some of the key things are downscaling global models to local. Okay, there's some challenges with it. Science teams are working hard on having a very good, decent resolution data being available at local scale. Processing big data, that has always been challenges, and now we're talking about big data in several terabytes. Just reading CMIP 6 now is, I think it's 30 terabytes or more. So that is probably where we have to lean on cloud infrastructure, or really even on-prem is fine, but in terms of the amount of computing that has to happen, it needs to have a very robust cyber infrastructure program. Creating analysis-ready local scale products. Again, this is a term that is used sometimes in terms of mostly Landsat-related data, ARD, analysis-ready. But as far as we are concerned, we're talking about stacks of time series data, images that are Earth observation data that need to be sliced and diced in a way that local communities can use it. We have to co-produce solution with stakeholders because they are the ones who know what the problems they're facing and what angle or what approach they should take to fight this mitigation adaptation challenge. And the open science infrastructure, which is, again, yes, you can leverage a non-open source or a proprietary product, but then how do you create open science out of that scene? We all know the risks when they're quantified, gets published. A lot of products are already out there. Fire risk from EUSTIS have excellent mapping, a front-end tool that has gone through this whole pipeline and now produces near real time with, of course, a 3-hour delay of fire risk. There's also health risk, which GMO at Goddard have put together a research product that can then be piped into air quality map or data product that can be plugged into a map that CDC currently is hosting on their data portal. Now, when we are communicating with stakeholders, we have various needs. Bob just mentioned his list of interests. We are targeting one at a time. The first one we are looking is the GeoCF forecast, 5-day forecast. And we are trying to at least put together a pipeline that can serve from point A to point B, where users at any point in that data pipeline are able to access this data either as raw format or in a slightly more curated format, where we do some value add in terms of what variables of interest their needs are, or in terms of the format or the file type, for example, that they are wanting. So we try to create this pipeline based on our assessment and our continuous engagement with stakeholder, and then they're able to pick the data at whatever point in that data pipeline that they're interested in. So this is an example of multidimensional data getting converted into GIS layers. This is a global data set. It's a NetCDF format. Slice it by time series based on the variables of interest. And once we have that, we upload all that data, including raw data, and also as separate GIS layers to AWS S3 buckets, and also make it available on a OpenGeo stack on cloud. I've listed their set of layers that they're interested in. The good thing about cataloging it this way is, one is of course open source. All they have to do is be able to access that catalog dashboard. And then on the right side here, you would see that they get to choose the format in which they would want to download that data set. So this is almost like a sliced and diced data product from this high-level multidimensional data that the science teams have created. And here at the bottom, you can see that it's also available as S3 object in Amazon. So the next step that we are trying to get to is the CIMIC 6 data, which is global downscale climate scenarios, and we are trying to get to that as a next step, and kind of similar to what we had done as far as data pipeline for GEOS model. But now the only thing is now this has to tie to some sort of application downstream. And one of the applications that we are currently getting started on, this would probably kickstart in August. We are lining up resources for this project is to incorporate climate risk into current socioeconomic risk that exists around Greenbelt, Maryland. So we've identified climate risk areas by census tracts. We've overlaid that with economic risk based on HUD data, as well as FEMA's climate risk data. And they've identified communities around Greenbelt. And then the next step would be approaching the municipalities and having them and providing them with a tailored, specific to their needs data product that could be taken right from CMIP 6 and in its curated form. So I'll leave with this chart here. So the socioeconomic pathways I had described earlier. There are these 5 narratives of how the society will be. We have to see where each community fits, where each of the groups fit, and the stakeholders have to identify where do they see themselves. Again, this is even at the global country level scaled, where you're talking about the middle of road where SSP2 is not much has changed. We continue with how we use. There's no induction of green energy, for example. The way we have continued historically is what we continue, and we hit at SSP2. Then again, where regional rivalry comes into play, ideally not good. The inequality, SSP4, those are not the best ways forward. Again, this is for each community to decide based on, are you up for mitigation? Do you have resources for it? Or are you up for adaptation? And how can you be in what group do you see yourself as? And depending on which, then they would approach various groups and then try to go from an approach where they have this global view of how their community should turn out to be the end of century, and where and what work that they have to do in order to reach that target. That's all I have. Thank you for your time.
Hi there. My name is Michi Tatsubori. I'm from Japan. I'm working for IBM Research in Tokyo, and I'm a manager of artificial intelligence research. Here, to be honest, I was not aware of this meeting several months ago, and so I'm not sure what is the expectation here. But let me raise a little bit question about the artificial intelligence, testing your intelligence. But so have you ever heard of ChatGPT? Yeah, yes. Do you know what is the technology behind ChatGPT? It's a kind of called foundation models. Have you ever heard of it? All right. Half of it. Okay, good, great. So yeah, I would like to mostly talk about the foundation models. And since I'm from the AI, and I would like to introduce the kind of takeaways here. We are going to the lots of pictures of advertisement. So takeaways for my talk is just, we are going to have foundation models, not only for ChatGPT or natural language processing, but for any data, including satellite data or whatever. So it changes the kind of how we should work with artificial intelligence or machine learning or data. So since we are talking about how we are going to use data, so this is what we are changing. It's not the 10 years later, it's coming in a few years, maybe in a few months. And so you see that how ChatGPT changed. You work with computer, right? And maybe some hate it, but it drastically changed how you interact with AI. Yeah, you can access and customize AI by yourself. Anyone actually can do that. It's coming. And actually the one great feature with so-called foundation models is it's allow the kind of low data situation. Low data means less data, less training data. I will explain a little bit later, which is good in terms of the kind of open science, in terms of inclusiveness. Usually the machine learning requires tons of supervising data or labels, hand label data. You need to teach machine how to do it. But teaching itself is too costly. Sometimes it's available, but in the most of cases, in a practice, it's not available. Maybe you can teach 10 times, but you cannot teach them a million times, right? But foundation models potentially allow you to do it few data training for training the machine models. So that's a kind of good part with foundation models in terms of inclusiveness. So more people can apply AI to your data, even it's few labels. But there's also a little bit, let's say the negative part. I can't really propose how to mitigate it, but there should be some difficulty and issues, especially in terms of the open science. So that's the kind of takeaways. So then the talk has been done, but I can do a little bit more details about the maybe 1 minute introduction about the foundation models. So it's a busy, but you don't really need to see the details, just to see the letters. So foundation models help machine learning with less labels, but how it's done. So what's happened with, actually, let me take the ChatGPT case. So ChatGPT is really kind of intelligent, right? Not truly. I know there's some limitation. Really, actually, for us, for scientists, it's still just a machine learning, but it looks great. But what makes it possible is so-called self-supervised learning with unlabeled data. So what's the trick behind the ChatGPT or so-called large language models is we give just a bunch of sentences. It's there. It's millions or trillions or data out there. We just give it to the machine, but let them learn from it by masking some portion of it to guess it. So that's a masking. It's not only a technique, but by doing so, we don't really need to label the data by ourselves. And machine started to learn by itself. And what happened is in the natural language processing, there's a kind of many researchers has been working on that. For example, that natural language task of translation, let's say translation. There's many language tasks like classification or whatever. But they put the kind of decades of effort to increase the performance of or accuracy of translation. And they are working, yeah, my research increased the accuracy 0.1%, 0.2%. They did it for decades. But when the large language model or foundation models comes in and some people applied it in a natural language tasks, then eventually it increased the performance in the kind of terms of like 10%, 20%, just by applying foundation models. So that's why it's called emerging, and actually you see it in the ChatGPT. It's not only that, but the bunch of engineering behind it, but it's the magic of foundation models. And what you can do is the same thing with, for example, in a satellite data, geospatial data. There's a bunch of data thanks to NASA, Copernicus, others. There's a bunch of data, but without labels, right? So what we can do is just give it to the machine. Maybe let them start self-supervised learning, masking some portion of it, so that they can understand by themselves about the, let's say, the satellite data. So this left-hand side part is one example of a self-supervised learning we have implemented, applying the same concept as the natural language processing in IBM. But it can be any arbitrary self-supervised learning. And what's done here is, let's say that we have our satellite data and some portion of them are masked. Let the model to guess or the complete the missing part somehow. And somehow the AI or this self-supervised run model run about the data here. So we picked some portion of it and put it to another machine learning task. In this case, it can be, for example, semantic segmentation task, like let's say, given the image, let's segment what is this part, like is this flooding part, or it's a kind of wildfire scar, or that kind of, it's called semantic segmentation. Or you can use it for the given the some data, some image, or maybe the image, and then give it for example, how much CO2 can be absorbed or maybe produced from that portion. That can not simple segmentation, but about guessing what is the value. It's called regression task. So there's a bunch of variant downstream tasks out there, and there are potentially opportunities that foundation models we trained without giving any labels can increase the performance of AI. So nowadays, we to say extremely, there's no science without AI. I'm right. I'm not sure, but so it's gonna be, but that AI part gonna be drastically changing with the foundation models, meaning that maybe, of course, there was a limitation with AI-based approaches, but maybe this foundation introduction of foundation models allows it to be practically available, or just increase the accuracy of their performance. Okay, so then I think you enough learned about the foundation models, and at least you understand that it's coming. It's coming. So once you understand it, my part is fine. Then it's a kind of advertisement that IBM and NASA is doing a lot with the data, especially with the data and building a foundation models right now. And actually, we have started. We have already have our own foundation models, and it's going to be released this year. We have picked up several applications of foundation models beyond language, but for the satellite data. Let's say, yeah, it's an advertisement. It's called Watson X, Watson X .ai. But it's not necessarily IBM. It is happening. Any kind of AI research. And here's a quick example or use case of what we are doing. So for the foundation models, we use the so-called HLS. HLS is a harmonized Landsat and Sentinel-2. It's basically the composition of US and European satellite data. And it's used without labels to train it. I will skip it, but the technical term here is 3D visual transformer. If you can say it, people think of, oh, you know, foundation models. The visual transformer is a kind of technical keyword here that it's used, and some sampling techniques used. But let me say much more quick examples. Yep. Let's say that this is the example with semantic segmentation, like flooding or fire scars, or more generally land use. It's a farm or forest or those. So what's happening here is that, so originally we applied so-called deep learning. Why it's called deep is we have a deep layers of neural networks. If you understand it, it's perfect. But instead of training it from scratch, for given the input, satellite data, and what's the expected prediction, in this case, for example, here is we have a flooding. If we give this as a labels and train the AI, it can predict the unseen satellite imagery. But what we can do with foundation models is, instead of training it from scratch, just replace this sample portion. In this case, it's called encoder, how to interpret the image, but with those trained with self-supervised learning as foundation models. That's the only thing. Other parts, pretty much same as the existing technology. So, but just applying this kind. Yep, let me skip some details, but yeah, for example, yeah, the takeaway is, for example, this is the IOU, meaning higher, better, in terms of the prediction. And right hand side is how much computing needed for training it. And this blue one is, and this dotted line, this dotted line is that those trained from scratch without foundation models, but kind of using let's say the hundreds of of epochs using very computing power and data. But what we can do is even by giving the half of data, we can still get the, this blue one here, we can get a better result than those without foundation models, okay? But even with the less labeled data, so this purple one still get the almost better result with the training data using fully leveraging the labeled data. So there's two things it can show, it can prove that it can go far better than existing supervised learning. And there are potentially opportunities you can do it with less data, all right? So that's a kind of quick proof for the case with the fraud mapping. So we did it with a fraud mapping and about biomass detection and wildfire score for this one. All right, but I think it's enough from me. Let me get back, but yep. So just bottom line, just repetition. Foundation model is coming. Don't forget. You never forget, right? And it changes how we interact with the data. But I'm not so sure yet. Sorry, I can't propose it. But how to do it within open source in open science, it's gonna be much more complicated actually. I don't show your answer. Actually, I don't have it. But let's think about it, considering it's happening. Okay, that's it. Thank you.
Hi, my name is Grace Llewellyn, and I'm a software engineer with the Digital Twins project at NASA Jet Propulsion Laboratory. An Earth digital twin is an interactive and integrated multi-domain, multi-scale digital replica of the state and temporal evolution of Earth systems. We are working to enable users to run hypothetical scenarios to improve our understanding, prediction of, and response to Earth system processes, natural phenomena, and human activities, as well as their many interactions. We are currently working on 2 digital twin projects, one for hydrology and one for air quality and wildfires. We are building our Earth system digital twin to be professional open source. This is a visualization of some factors that go into our digital twin framework, such as a simulation and numerical models, AI, real-time, scalable visualization, and multi-computing. Some tools we are using to develop our framework are Apache SDAP and the open source On-Earth software, which is used by NASA Gibbs and Worldview. This is an architectural diagram for digital twins, where the blue side is the physical world and the yellow side is its visual representation. The inside boxes are the functionality for digital twins with arrows connecting them. This is integrated in a continuous loop, but you can see the break between the physical world and its visual representation. The outcome of this loop is forecast predictions, like where water discharge is going, etc. We are not trying to create just a plot, but also actions that we can take, such as telling people to wear a mask or stay indoors. We promote standards for our data, like STAC and OGC. We are pushing our own standards as well through open source, for example, for Hofmuller charts and other statistical time series. We have a community of all open source using the same APIs to make accessing our system easier for users. For this project, we have paired with the French Space Agency, CNES, as well as other NASA centers, Serifax, CLS, Quantiq, and Vortex.io. Our collaboration between our project and CNES's project, Space for Climate Observatory, SCO, is focused on establishing a federated digital twin solution. Some outputs we are expecting to produce are flood alert systems and risk maps. We also have a website with more of this information at ideas-digitaltwin.jpl.nasa.gov/floods. A great model of our work is our generalized Jupyter Notebook, which demos our back-end capabilities through use cases. Some of these use cases include the Mississippi River, the Garonne River in France, Hurricane Ian in Florida, and the flooding in Pakistan in the summer of 2022. Here we have some sample graphs from the Garonne River generated in our Jupyter Notebook. Included is output from Rapid, which is our model that estimates river reach discharge using land, surface, model surface, and subsurface data. Our Jupyter Notebook is open source and can be downloaded on our website. Another great model of our work is our VR modeling capabilities. The immersive and interactive capabilities of VR allow us to step into simulations and experience scientific concepts in unprecedented ways. The use case for this example is the Garonne River in France. Here you can see we are changing the depth. And we can also change the color bars you can see in the next step in the bottom right. This is our use case for Hurricane Ian. And in the top part of that box there, you can see the region of Florida that is selected, where the variable we are looking at is precipitation. The other digital twin that we are creating is our analysis collaborative framework for air quality. Some motivations for AQACF are demonstrating analysis applications by focusing on air pollution in large cities and establishing an integrated cloud platform for interactive on-demand data analysis and visualization. Some of the goals of AQACF are harmonizing data management, analysis, and visualization through our three sources of data: satellite, model, and in situ. Our three production quality applications are our web-based data analysis tool, our generalized Jupyter Notebook for an API tutorial, and our VR-powered immersive science. For both the air quality and flood digital twins, we are limited in the amount of in situ data we can ingest into the system for immediate analysis. Therefore, we use the data already ingested in a machine learning model trained on historical data to predict particular sites of interest, for example, imminent flooding or poor air quality risks. This approach to prioritizing in situ data ingestion ensures that the most relevant data is fetched and available for analysis for flooding or poor air quality events as soon as possible, whilst staying within a budget for data ingress and storage. We have another web page for our air quality project at ideas-digitaltwin.jpl.nasa.gov/AQACF. For our air quality digital twin, we are working with the Deputy Mayor for Budget and Innovation for Los Angeles as our PI for our Predict What We Breathe project. For Predict What We Breathe, our collaborators at Cal State LA have developed multiple predictive AI models for various pollutants species such as PM 2.5, ozone, and NO2. The models and output predictions are integrated into our digital twin. Some of our other customers and stakeholders include scientists from various disciplines, data centers, and policymakers. Next, we have a demo of our data analysis tool. And here you can see we are selecting the layer for the ozone global tropomi, and we can change the color maps in the top corner there, as well as change the range of values through our slider. And you can set the squash on and off to change what values are shown. And you can add a second layer, or multiple layers, but here we're adding a second layer. And you can switch which layer is on top by changing the order in our active layers menu. And on the top layer, you can change the opacity in order to better see the layer underneath. Now we're going to switch over to our analysis tab, turn on the in situ stations. We're going to choose one for Queens, draw a box around that region, and then again, select comparison data for that box. And now we're generating a chart here, and in the top, you can play an animation, which will go over the dates for that chart, and you can see the map imagery in the background changing. If we stop that animation, we're able to jump to a specific date and time, and the map imagery will change to be that date and time as well. Our digital twin projects incorporate action science through estimating potential risks as a result of wildfires or floods, retasking an Earth orbit instrument, acquiring new in situ measurements, dispatching a UAV, and generating new analysis products. In conclusion, it would be too complex to model the entire Earth system by a single digital twin, but we can build bridges between our digital twin islands to best create an overarching framework. Thank you for your time.
It's discussion time. Thank you. A few more minutes. You have specific topics. What do you? What? Okay. So just helping out. I'm Jennifer Wei. I think this is my first time joining this ECIP summer, and I think I heard about from Stephanie. Sort of in the beginning, what is this session's purpose? And then sort of following all these wonderful speakers, what you talking about, and then I jotted down like all the points that sort of tackling what Stephanie said, so this is about, all of us working together from the NASA side, whether you're a scientist, or data engineer, you're trying to come up with the solutions, or your local stakeholders, and local stakeholders working with NASA, coming out with different infrastructure, and coming from the private sector, the IBM using the AI. I think it's sort of the key is what is that we trying to solve, and actually. I just have a very simple comment is when I think during the 80s, I grew up in Asia. We have a song, it's called literally translated to like, tomorrow will be better. However, due to the climate change, I think we need to stop having this thought, because whether tomorrow will be better or not, we know it won't be, because climate change is impacting now. It's impacting everywhere from global to local. So how can we work together? I think I really appreciate everybody's talk and chime in, but this is the time how, we can, any question so far. And I hope people can monitor if Stephanie had online have questions. So question time. Have you heard about all this wonderful, needs, solution given? Have you wondered what are they different? Have you even thought about some of the infrastructure might be similar and why they still developing? And then I think earlier we heard about open science, and then, what is the challenges here? And then people will say, I wish we know earlier, so we don't need to put so many eggs in the different baskets. Is this a good solution? I want to hear from you guys.
Yeah, thank you, Jennifer. I can't see the room, but if nobody has their hand up, maybe I'll just chime in for a second. Can you hear me?
Go for it, Stephanie.
Okay, yeah, I just wanted to thank all of the speakers who did a really nice job showing how, this is a really big challenge. And so informing decisions around climate risk is not trivial. Taking all of our model information and all of our satellite information at global scale and bringing it down to the local application and decision level, it's a Herculean task, and it really takes a village or a whole community of effort, ranging from the the engineers and the data scientists who are building the instruments, pulling data into different platforms, to the systems where they're integrating the local information and working with those local decision makers to figure out what they need for their decisions. So this is a relatively new space for NASA to be getting into. We really appreciate organizations like Western Pennsylvania Regional Data Center, because they help us to reach a broader audience. At the same time that all of the new technology coming online with machine learning and artificial intelligence that Nishi and Grace discussed are opening up a lot of possibilities for creating things like digital twin. And so, yeah, I don't know if anybody in the audience has a question yet, but I just, I really appreciate the diversity of the speakers in this panel and all of the various challenges and the barriers, like Bob mentioned. And yeah, anybody have their hand up?
We do have people. Okay.
As a former librarian, I was really I was just wondering what types of users are coming into the platform. 12, are you dealing planning board, all, and how do you handle that diversity?
Yeah, so in terms of users of data, it's really a big mix. So it could be everything from a community organization needing a piece of information to put into a grant proposal, all the way through one of our academic partners looking for the right data set to incorporate into their research. But I think like for data like this, it's going to be at a municipal level, a county level, and then at the university also, with researchers that just like want to be able to pull data in. So I think like it's really important for this community to engage with academic librarians, for example, so that they know about all the resources and all the different tools and the training that's available, so they can communicate it through their networks in their own institutions. I think like where we are, we're kind of like in the middle of a lot of different things, so we can pull use cases from organizations and even nonprofits that work in this space. So it's a big mix, but I think for this community, it's a lot of like larger scale nonprofits with maybe a little bit more capacity to address things, maybe activist organizations, academic organizations, and local government.
Can you sort of mention, just for people here don't know you? So,
So yeah, my name's Tom Paris. I'm president of a local firm here called iSciences. We're a geospatial data analytics firm.
thank you.
Yes, I'll keep you on the spot here, Bob. So I think you've seen a lot of interesting stuff that's going on sort of in the broader NASA Earth data ecosystem. And so I guess I was hoping to sort of get two things from you. What are the things of what you maybe saw today, or just in generally in the Earth science data system at NASA, that sort of most excite you, that feel like these are the things that we're going in the right direction for user engagement? And where is it that we've completely missed, where we're just completely wrong, where it's a waste of time, we think this is user engagement, but it's actually just a total failure? And you got to answer both. I'm going to hold you to that second one.
Yeah, I think, as somebody who went to like planning school, the science of this is not, I'm not there every day, but I'm thinking about like, oh, how can people that we interact with make use of this great stuff? So it's all great. The challenge that I have is like, okay, yeah, what are the use cases? How do I connect it? Who connects the users to that? And I think like thinking about how you engage people, really focus on those relationships. Don't just think that the next chatbot or the next form on the website is going to kind of make that connection. You got to get out there, do the work, engage with communities, because not everybody's online in the way that you're all online. Not everybody's going to interact with the kind of platforms and the tools that you have. Not everybody even knows how to ask the right questions. And so I think if you think about who engages, who can you partner with, like organizations like us all around the country and the world that can have those relationships. You don't have to have that, but you can kind of come and say, oh, what kind of things can we help with? What can we do? And how do we organize our work around those kind of opportunities is what I would suggest. I hope I answered both.
Yeah, and maybe I'll just chime in. We started this discussion with Bob and Western Pennsylvania Regional Data Center over a year ago, and it takes time to iterate and share some of the things we have, talk to them about what are the things their region is concerned about, what are the data sets they need, where can we sort of come together to provide data. And now McCool has been working a lot with David Walker to figure out, do we push the data to them or do they pull it? So there's a lot of iteration in this co-production of a solution for them. And then I'll mention one last example of this in our upcoming project with the area around NASA Goddard Greenbelt. We're hiring somebody who's going to work directly with some of the local planning people, specifically around sort of their stormwater infrastructure and helping them prepare for the next 30 to 50 years of what's projected, and helping to interpret what's coming out of the climate models and the uncertainties, and figuring out what form they need that information to inform those decisions. And that'll be an iteration. And again, McCool will be helping with that to figure out, can they work with GIS layers or do they need Excel spreadsheets or some other format?
Great. Any other question, concern, challenging the speakers from this audience? I don't want to put Bob on the spot all the time, but really, I think this is a great opportunity to sort of openly discuss, and let's really figure out how can we go from here, knowing what we know. And as I'm talking and walking toward, I'm so sorry. I'm thinking.
This is a question. Hi, I am Eli Holmes. I am with NOAA Fisheries. And this is a question for the last speaker and the very last demo. And then I guess this is a kind of a general question for those who create interfaces like that. I like, I know of Fisheries, we also create some like user interfaces to our data where the user is doing a lot of like manual things and creating boxes and layers, and it's super powerful and people really like that. It's a really great way to get information to them. But one thing I think about is how do we ensure reproducibility so that the user, when they come back, maybe a different user is trying to replicate what they created, or they themselves are coming back, a month later or a year later, and they're trying to reproduce that. So just kind of thoughts of what are the approaches?
I think great question. There are a lot of sessions concurrently or throughout this week addressing your question, but I'll let Grace answer your question.
Yeah, that was a good question. Thank you. So for one example where I drew the box earlier, there's different ways to change the exact latitude and longitude of that bounding box. So instead of just like randomly drawing a box, you can make sure to get the exact same numbers. And with the analysis chart, I didn't demo it, but there is a way to download that data. So when you download it, it would also have those coordinates of the box in it so that you could, like if you saved that to your computer and then a year later came back and wanted to recreate exactly that, you could use the same latitude and longitude to the exact same box and see the information on that in situ station, which I selected as well in that downloaded chart. And For in terms of creating different deployments of this and making it reproducible for other projects. Right now, that was just an example for air quality, but we are planning on having a deployment for floods, which is our other digital twin coming out hopefully in the next couple of months. So the project has definitely been designed to make it easy to switch between the different projects so that you can have multiple different projects using this exact same data analysis tool, which was created with the source code from the sea level change portal, if you all are familiar with that as well.
I think that like one thing that we've struggled with is how to make sure that people they're using the same data as before, especially when we've got these really large data sets and they are getting updated for a variety of reasons. And to be able to target the moment that person hit the database, is it possible to go back in time and actually redo the exact analysis?
Repeating the question for those online, is there a way to repeat that exact analysis for that moment in time that the user generated that analysis? And at the moment, we do not have that capability. But ideally our map imagery layers aren't changing too much. If they remain on the tool, then that is, since only a couple of them are models, like the ones that are just satellite data. I'm not sure the ways in which that those would change over the course of a year. I would imagine if you're doing the exact same bounding box for the same time series analysis and for the same dates, that it would return the same data, unless you know of some examples, which that might not be the case for satellite data, that the data could change over the period of a year or so.
Yeah, I'm thinking about satellite data. We're talking about algorithm. There's some process involved, and that maybe errors were detected, or the algorithm being used to process the data we've never seen before. I guess like a new version of that data, like in my mind, because we haven't introduced to it. Exactly, sometimes the versioning of the data process part. You're thinking like my data provenance, like which data version I work with. Right, yeah, and it's a hard problem.
Yeah, that's definitely something I could bring up with my team. And it seems like versioning might be the answer, that if it was rerun through this algorithm, the satellite data, then we could just have our version, for example, 1, which stays on there, and then like have version 2. But then I guess you would need to know that you previously did it with version 1. So it's just always called version 1 initially or something, and then work from there.
Yes. Like a data with metadata, right? So it's just as it's being pulled into the system as a digital and just capturing that initial metadata of the data you're working with. So that when you go back and say, what did I use last a year ago? You can see that maybe there's a way to say, hey, there's a new version of this. That's an improved version. I want to use that in your workflow.
Yeah.
So actually, this is a very good question. Sorry, can I?
I think in terms of reproducibility, that's actually there's a concurrent session is about information quality cluster that ECF actually has been trying to address this issue. So I think this is a very good question, and reproducibility following the fair data principle. How can we do it from different aspects, whether you're a data producer, your data or the implementators and what have you. This quality, the information system, especially coming from NASA, this is what we're advocating, I think is the key, but it's hard to get to. But I think this information quality cluster, they're currently addressing one of your concern in terms of reproducibility. But I want to sort of tackle this is actually for this group in terms of reproducibility, but I want to see the scalability, right? Because we hear some of you sort of talking about like digital twins, you have air quality. Bob, you mentioned you from the Pennsylvania local stakeholders, you looking at air quality as well. And maybe IBM, since you're Watson, right? So IBM Watson sort of empowering the whole weather system forecasting. So I was wondering, under the open science, open source science infrastructure, would this be sort of scalable? Can it be easily to adapt it based on specific user needs? Like, I work with the Chicago people. They also address air quality. Vermont, the air quality today is really worse than yesterday. So having all these already wonderful solutions, is it easy for us to sort of adopt it and or scale up from different user needs? I just want to sort of open up and see if anybody have some kind of comments or solution or suggestion.
Jennifer, I can't see the room. If nobody's talking, I might jump in and say something.
Yes, please.
Yeah. So
the-
these intermediate organizations like Western Pennsylvania Regional Data Center, they are really critical to scaling up, looking for organizations like these. As much as I appreciate Bob Gradick's suggestion that we ourselves go to all of these smaller meetings, there's no physical way we can do that. So we really have to look for these groups like them that can serve as intermediaries to reach broader audiences. We can do that, and then we can write up how we did it, and that can give ideas to others. But finding these groups that work directly with a large audience of their own end users and working with them, I think is really key.
Yeah, and Stephanie, what I was suggesting was, engaging with different communities of practice. So, we go and we meet with like 30, 35 partners of ours that work in local communities, but aren't local government. But then we also are like adjacent to chief data officer networks. And so like engaging and just saying, hey, we're here, we exist even on a webinar, and here's what you can come to us for, and here's how to connect. I think it's like one of those things that I would suggest is you can cover, 50 cities, 50 states by going to one meeting. And I think that would be kind of a decent return in that investment.
Yeah, I agree. That makes sense. Thanks. And I'll also mention the Greenbelt project that we're doing it's for learning, and there's no way we could do that with every town and municipality in the country. So, we're doing it to be a good neighbor at NASA Goddard, but then we will write it up, and hopefully that can be scaled to other places by others.
Yes. So I think this is, the thing is, let's talk about it, right? Because like Stephanie said, we cannot reach out, we cannot go to all the meetings, right? From smaller community, even from the K-12 schools to all the way to international, right? But, without this very first step, you're here. Let's talk about it. Let's learn from each other. How can we leverage what we have done individually, and how can we partner together and come up with a new solution, right? So if you have not spoken up, please, you can tell us who you are and tell us what's your need, and maybe there's already a solution that you're not aware of. It's really what Bob said, awareness. We don't know each other, and maybe if you want to know what NASA has, we know what NASA has, and because we didn't know this is what you need, we didn't talk about this. So if you want to speak up and introduce your problem, this is what this meeting is about. Don't be shy. Come on. Anybody? Oh, okay. Just a couple more minutes. Come on. This is the great opportunity. Come on. Come on. Yes. Yeah, I'll pass it. Introduce who you are.
Yeah, my name's Mike Johnson. I work for a company called Linker, and we are primary contractors with the Weather Service and Office of Water Prediction. So one of our big mandates is how do you build and then disseminate both operational hydrology models and then flood forecasts from them. but kind of working between agencies is a bit of a hassle, I think, if you're a Fed in general, and even more so if you're a contractor working for the Fed. And we've had a good collaborative arrangement between NOAA and USGS, because I had a USGS member on my committee. If that hadn't been there in that relationship before, that would have probably not happened. So from the NASA perspective or any other groups in the room, how do we get more synergy between federal groups that all have their own mission and are already probably understaffed to meet them? But there's clearly nice ways that they could relate to each other, like the flood forecasting one that you're showing from the digital twins. Clearly, there's some nice work on there.
If nobody else is speaking up, maybe I'll just say, you just touched on a really critical issue that's been brought up in a lot of high-level discussions through OSTP. We had a climate summit, an internal NASA-wide climate summit last December, and interagency, coordination is something that's top of mind for a lot of us. It's also challenging because taking a lot of tracking a lot of these things takes a lot of effort and energy, but we're trying to do it on the topic of climate. There is USGCRP has been tasked with better coordinating all the different federal efforts. So yeah, that's a big issue, and it's recognized that it's a challenge.
I know we're tired and we're on top of the hour, but luckily this is the beginning, the first day of the ECIP. We're here. Let's connect. Let's talk to each other and thank you. And I'll give the time to Makul or Stephanie. Good.
Yeah, just the can't hear you.
All right. So thank you, Stephanie. We'll continue to be here to connect with each other, and we'll try to bring out what will be the action coming out of this discussion. And thank you all. And if we have not talked to you, talk to us, talk to the presenters, and let us get to know each other. Thank you so much.
Thank you, and thank you, Jennifer, for moderating here. Appreciate it.
No worries.
Take care.